Okay, welcome back. Last week we saw how to translate the maximum a posteriori problem, the inference problem, on any undirected probabilistic graphical model, on any discrete undirected probabilistic graphical model, into an integer linear program. Unfortunately, these are in general too expensive to solve. So we need to resort either to approximations or to models with special, more friendly structure. And this is what we will look at today. So a subclass of undirected probabilistic graphical models that do make inference particularly easy. And these are the tree-shaped probabilistic graphic models. As a motivation, again, let's look at this semantic segmentation problem here. We have a couple of layers. We are interested in segmenting all of them. We can train a classifier to give us locally an opinion about which of the classes is prevalent. And then we have some prior knowledge, namely which label can be adjacent to which other as we transverse the image along one column. And we've seen that we can express or model this in terms of a Markov random field here painted over just 9 pixels. And we're interested, given our prior knowledge, which is encoded by these pairwise factors, and given the local estimate of our classifier, in finding the globally most likely posterior solution. And today, let's just look at a single column here. So we're going to concentrate on just one column out of this Markov random field, and later we'll look at how to get something useful on the entire MRF. So I'm going to draw this out just to be extra clear. I've shown 3 random variables. They are connected by pairwise factors, and this pairwise factor can, for example, look like this. So normally we want to learn this from data, but I've now invented a pairwise factor, namely one which says if, let's say, we just look at 3 classes. Let's look at classes A, B, and C. Up in the image, we had something like 9 or 10 classes. I just don't want to draw such a big matrix. So let's look at 3 classes. And let's say that I need to pay 0 penalty if class A is next to class A along this column in the image, or if class B is next to class B, or if class C is next to class C. So I leverage 0 penalty on this. Now let's say that here this is for I and this is for J. Let's say that if we go down from top to bottom, so I'm labeling these random variables here 1, 2, and 3. As we go from top to bottom, I never want to encounter class B after I have already encountered class A. So I'm giving a large penalty here for having either class B or class C below class A. And same for class B. So if I had just used this matrix here with 0 everywhere else, I would impose an ordering relation. It's not a hard constraint because the penalty is only 100. It's not, it's not infinite, but that's a pretty strong penalty. Now, moreover, I want some smoothness prior. So let's say a transition from class A to B has a cost of 1, transition from class B to class C has a cost of 1, and the transition from A to C directly has a cost of 5. Okay?
Why it's not a symmetric matrix?
Because I want to, so let me figure out which way now is top and bottom. So what this matrix says is, up in the image here, where I'm now considering only 3 classes and not 9 or something, it is legal to have A, B, and C, but it's not legal to have, let's say, an island of B up here. Because if I had an island of class B up here, then as I go from top to bottom, I would find class A, then class B, and then I would find class A again. And this I want to rule out by making the matrix asymmetric and giving a penalty of 100 for this. So we're going down, we're looking at a single column of the image. And here I pay a penalty of 0, 0, 0, because class A is next to class B. Then I pay a penalty of 1 as I transition from A to B. And I pay a penalty of 1 as I transition from B to C. If I had somewhere direct contact between class A and class C, like this, here I would pay penalty 0, then I would pay penalty of 5, and then again penalty of 0. So this model encourages to always have A and C separated by a layer of B. And this penalty of 100 says that I really don't want any class B above class A. So A to B transition as I go down is fine, but B to A transition is forbidden. And I charge you $100 each time that happens.
So then we can keep this structure.
So I want to segment this image, and I have some prior knowledge about which class, this is a retina image. So I know that in a healthy patient, there's always this kind of layer above that kind of layer. And this prior knowledge I want to bring into my segmentation model. And using this asymmetric matrix is my way of doing that. Who has a problem with that? Yeah, so can you ask a question?
I just don't see why the matrix is, because so far we always had symmetric matrices.
Did we have always symmetric? Okay, Sven says yes. Okay, today we don't. No, but is the point clear? So as I go down the image, yeah, transition A to B is allowed, but B to A is not allowed. And this is what I try to express in this asymmetric matrix here. More questions about this?
So,
yeah.
The opposite, if I want to make that it's allowed in both directions, then I can choose the symmetric matrix.
Yeah, so for example, if I used a symmetric matrix like this, 0, 0, 0, 1, then I would say A to A is fine, B to B is fine, C to C is fine, A to B or B to C is okay, just $1 penalty. Direct A to C transition is undesired. That gives you a $5 penalty. Yeah?
Here we assume that the transition is from I to J.
Yeah, so I've numbered my random variables. The one on top I've called 1, and the second I've called 2, and the third I've called 3. And I have here in this matrix, I've defined that I is the index which goes over the rows, and J is the index which goes over the columns of the matrix. Yeah? Here, up here, I said what is what. Make sense?
And also the rows of the matrix is the rows of the structure, what you call it.
So this is psi ij for I and j being neighbors in the graph. Yeah? So in this case, this is psi 1, 2. And I also claim, I'm using the same throughout. I'm saying that this is also psi 2, 3. Okay, this here is psi 1, 2, and this is psi 2, 3. And I'm using the same one because I want to use the same parameters in the whole image. Otherwise, I would need, millions of parameters, and I don't want that. Okay, and here I have invented these numbers, which, until quite recently was really state of the art. Yeah? So you have some prior knowledge, and then you experiment if you make the big number 100 or if you make it 1,000 or something. Yeah? But today, of course, we try to learn these numbers, but we're not quite there yet at the learning, because to learn, we need to solve inference repeatedly, and to be able to do that, we need to know how to make inference cheap, and that's what today is about. Yeah? So how to find the optimal solution with little computational effort. More questions?
Can you say again why the 5? I mean, you put a 5. And what you have made.
Why did I put a 5 here in this corner?
You want to encourage?
So I put a 5 because I said transition A to B is not great, but it's okay. Because if I did not allow transitions, then I would label the whole image with one class, which would be boring. But I usually know that there is an order of layers, A, B, C. And so by making the A to C transition expensive, I gave it 5, I could have given it 20 or something. By making this expensive, I say the model should preferably try to label a few pixels as B in between. Yeah? So the numbers I completely made up. I just tried to sketch, what does this model try to express? Yeah?
And the number of the penalty, does it affect the calculation?
Yes.
Yes, okay.
So, if I choose a much bigger number than 100, if I choose 10 million or something, that becomes a hard constraint. As I make the number smaller and smaller, it becomes a soft constraint. It's still undesirable, but maybe okay to occasionally have an exception to what I was just saying. And why do I want to allow so why didn't I not make it 1 million? Because maybe you have a patient, let's say a healthy person has A, B, C, but maybe a sick person can have A, B, C. And now you see, as I go down this column, I have a transition from A back to B. And if I completely rule it out, then my model is unable to find the segmentation. Then my model would always find this segmentation. Yeah? It would cut off this indentation. Okay, so this is why I did not make it a hard constraint.
Can I ask something? I mean, now the layers are like that.
Yes.
They were like this.
Okay.
The matrix is the same.
So here I've been talking about the pairwise interaction for the columns of the image. Yeah. Let me call this psi v for vertical. And now tell me yourself, yeah? Let's say for the same problem here, for this I segmentation problem, what kind of potential would you propose for the rows? Would you have it symmetric or asymmetric?
Symmetric.
Yeah. So for the lines, for the rows here, we would also have a smoothness prior. Yeah, so we would have 0 on the diagonal and some non-zero number off the diagonal. But you see, yeah, as I go from left to right here, let's say this is class B, and then I have class A, and then I have class B again. This is legal here. Yeah? So I would use a different potential for the rows and for the columns. So this would be here a horizontal potential, and this one would be a vertical potential and a vertical potential. More questions? Okay. So I have invented we're looking at just a vertical column here, and I have invented this pairwise potential, for better or for worse. And now I am also inventing unary potentials. I'm just saying that, this is psi1, psi2, and psi3. And I'm just claiming that the classifier at this pixel said that the first class has a cost of 1, and the other two classes have a cost of 3 each. And here, let's say the cost was 1 to 1. And let's say here the cost was 2 to 1. Yeah, so the first classifier tells me that it believes that class A is found at this pixel because A has the lowest energy. It has an energy of 1, whereas B and C have an energy of 3. Yeah, so these are the energy contributions for class A, B, and C from this unary potential. So the first pixel would vote for class 1. The second pixel is undecided. It would vote for either class 1 or class 3. And the third pixel would vote for class 3. If we only took into account these unary potentials. But we also have the pairwise potential, so we need to figure out how the entire system behaves. And now I don't like these unary potentials dangling off the structure here. Yeah? So I want to translate this in a somewhat simpler structure for reasons that will become clear. Yeah? So I'm saying this is random variable number 1. I could also call this Z1. And you make this big so you have enough space. Z2. And Z3. So my question is, the model on top, can we translate this somehow into the model at the bottom without changing anything? I have some energy function here, some energy function defined over Z1, Z2, and Z3, and I want this energy function to be the same in the bottom model. So my question is, can I absorb the unary potentials in the pairwise?
I guess we could somehow add the unary energies to the pairwise ones. For instance, when you have the first two random variables, and let's say the first one, consider the first one being state A, the second one being state C, for instance, then we go into the matrix of that pairwise potential and add to the first row and third column the energies of the two.
Yep, this is exactly right. So it's always possible to absorb lower order potentials in higher order potentials, but not the other way around. Yeah? So higher order factors, typically you cannot write in terms of lower, or you cannot decompose them into lower order factors, because if we could, then why would you have introduced this higher order factor in the first place? So let's do what you suggested. so I'm creating here a new potential, which I'm calling psi12 tilde, and I'm saying this is the old potential psi12 plus I'm now absorbing in it the unary potential associated with the first node, and I'm associating with it the unary potential of the second node. And similarly here, I'm calling this psi23 tilde, and I'm saying this is the old pairwise potential plus the unary potential associated with the third node. And you see I have a bit of an asymmetry here, yeah, because here I have 3 terms and there I have 2, but never mind. Okay, so let's, okay, I need to write this a bit more cleanly because I have a dimension mismatch here, yeah, psi12 is a matrix and psi1 is just a vector. So we said that the first index refers to the rows, so I'm going to, I'm going to multiply this column vector here with a row vector of 1s, and do like that. And similarly here, I have 1 psi3 transpose. Okay, so let's do this for real. Yeah. So psi12, I'm just copying from the top, was 0, 1, 5, 100, 0, 1, 100, 100, 0. This was psi12 plus. Now my vector psi1 was 1, 3, 3. And I'm multiplying it with a row vector of 1s to replicate it, and this gives me 1, 3, 3, 1, 3, 3, 1, 3, 3. This was the first potential, or the first unary potential that I've added here, and now we have also a matrix for the second unary potential, which is now a column vector of 1s multiplied with the second potential was 1, 2, 1. Okay, and thus I get my new overall pairwise potential, which is 2, 4, 7, 104, 5, 4, 104, 105, and 4. Everybody fine with that?
Why for the tilde phi12 we consider the 2 prior term, but for the tilde phi23 we just consider 1.
Okay, so I could also have done this. I could have added 1/2, so 1 is a vector, excuse me. I could have done like this, yeah, 1/2 here, and I could have added the other half of this potential down here. I could have distributed it evenly or fairly, yeah, but the only reason I haven't done that is because then I get fractional numbers in my matrix, and I didn't want to write decimal points. Okay, so you're completely right. I'm assigning this potential here and this potential here and this one there. This construction is asymmetric, and I've done it asymmetrically just to avoid dealing with fractional numbers.
And by writing in this form, it means it's biased.
No, it is not biased because the old energy function is exactly identical to the new energy function. Yeah? So I have here now an energy function Z1, Z2, Z3, which is psi12 tilde Z1, Z2 plus psi23 tilde Z1, Z2. And if you look at these equations, or you know how we have defined this term and that term, you will see that it's exactly equivalent to the energy function which we had above, which I can write down for completeness. Yeah? So this is only for neighboring I and j. There you go. So there's no bias, okay? Good. So let's just get this second matrix here for completeness, and because we'll need it in a moment. So again, I have 0, 1, 5, 100, 0, 1, 100, 100, and 0. And now I add to it 2, 2, 1. And I get a new effective pairwise factor with the following entries. Okay. Good. So, why don't we always do it? The second model looks, in terms of the graphical model here, this looks simpler than the first. So why don't we always write the models like this? Well, the reason is that above, I could use the same pairwise factor everywhere, and it's just the unary factors that differed. And here now, my two pairwise factors are no longer the same. So this is why I don't always use this representation. But for now, or in what follows, it will make my life simpler. Everybody okay so far? Good.
There's one mistake in the first matrix.
Thank you.
1, 3 should be a 5.
In the first matrix, in this one here?
No, and the result.
In the result, the 3 should be a 5. This one?
No, sorry. The fourth one on the first line. So 1, 2. Yes, this one. And now an element 1, 3 should be a 5. Right? Or 2, 3. What is it? Am I wrong?
2, 3 should be a 5.
2, 3. Yeah, 2, 3. Sorry.
This element 2, this element here is wrong. It should be a 5. Thank you very much. Thank you. Okay, so now, so far, we still haven't found the global solution, which is what we're after. The algorithm that we're going to use for this is a shortest path algorithm, Dijkstra's algorithm. Who knows Dijkstra's algorithm? 1, 2. Okay, so I'll do it for the sake of the others. Okay. So we start with an excursion. Shortest path computation. And this is a representative of one of the very fundamental algorithms in computer science. Yeah? So dynamic programming is one of the most important ideas in all of computer science. And the basic idea is this. Let's consider a trellis. So a trellis is a regular graph. And I'm considering here a directed graph where I have possible transitions as indicated here. And now bear with me, this graph will become much denser. And now it gets its final touches. So in essence, I have sorted these nodes by row, and I am allowed to make a transition from each node to every node in the following row. We have a source, and we have a target, and we have weights associated with these edges. I am making up some weights. So let's say this edge here has a cost of 1, this one has a cost of 3, this one has a cost of 5, and let's say this one here has a cost of 3, and this one of 5, and this one of 3, and here I've been forgetting some edges. Let's make this one a cost of 2, and that one a cost of 4, and I'm sparing you more. Okay, it's just to show the principles. Okay, and we're now looking for so each of these edges has a cost, and we're looking for the shortest path from source to target.
Does cost means the energy?
Yeah, let's say cost is energy. Yeah, so lower is better. Okay. And the cost of a path is the sum of the cost of all the edges along that path. And now I can ask this question recursively. Yeah? So if I want to find the minimal cost to, let me write the minimal cost to the target, then I can say that this will be the minimum of, okay, let me number the nodes. I'm calling this one 1, 2, 3, and then 4, 5, 6. This one is 7, 8, 9, and this one is 10, 11, and 12. So how do I get to the target? I can either get to the target by traversing point 10. So I need to pay at least the minimal cost of getting to node 10 plus a transition cost of 1, yeah, because I pay 1 to go from node 10 to node T. Or, can you continue for me? Yeah, I need to pay at least the cost of reaching node number 11, the minimal cost to reach node number 11 plus 3, or the minimal cost of reaching node 12 plus 5. Yeah, so if M always means minimal cost, do we agree that this is the minimal cost of reaching T? Yeah. These are the only possibilities of reaching T, and we know how to compute them given that the cost of a path is additive over the edges. Okay, fine. Then let's look at these things in turn. Yeah? So I have M10 in there. M10 is, I can reach M10 in 3 ways. Somebody? M7 plus 5, or M8 plus, what is it, 2? Or M9 plus, I have not invented anything yet, let's say plus 7. And now we have M10 here, and we also need M11. Yeah? M11 is the minimum of, how do we reach 11? Via node 7 plus 3, or via node 8 plus 4, or via node 9 plus, let's say, 8. Okay. And now we see something here, namely, here we call for M7, and there we also call for M7. And here we call for M8, and there we also call for M8. Yeah, so we need to compute the cost M7 only once, but we can use it repeatedly. And the same for the cost of M8. And this is a property which is called, so these are overlapping subproblems. And I can now recurse this, yeah? So I can continue that, excuse me, that M12 equals the minimum of something, yeah, and then I will find this. And then I continue that M7 is the minimum of something, and so on and so on. Yeah? And this recursion here would also be called a top-down approach to dynamic programming. Yeah? So I start from the desired result, and then I ask, what problems do I need to solve? And then I solve these problems recursively. So if we go in this direction here, by asking questions, this would be top-down dynamic programming. And actually we need, for dynamic programming to work, we need two conditions. One condition is that our subproblems are overlapping, and the other condition is called optimal substructure. And I'll show you in a moment what this means. So whenever a problem has optimal substructure and overlapping subproblems, then you can use dynamic programming. What this means is that let's assume that the cheapest path to T goes through, let's say it goes through this node here. Then, so the cheapest path to T I'm claiming goes through the fat green node, which is node number 8. Then optimal substructure means that the shortest path to node 8 must also be the one that in the end will lead to T. Yeah, so if the overall optimal path from S to T goes through 8, then the best path to 8 itself coincides with that solution. Because, you know, if there was a second cheaper path to node 8, so if the red one was cheaper than the top of the green path, well, then I would replace the top of the green path by the red one, because the system has no memory. Okay? So this is called optimal substructure. That was the top-down approach, but when you program recursively, you always have a big memory of things, a big overhead of things that you need to keep in memory and so on. So the preferred approach, if you know how to implement it, is bottom-up dynamic programming. And Dijkstra's algorithm is an example of this. So Dijkstra's algorithm starts at the source, and then it finds the cheapest path to the first 3 nodes. And you know, there's not much to do, so there's just a unique possible path to each of the first 3 nodes. And then it asks what is the cheapest way to, I had some edges missing here in my graph. Then it asks what is the cheapest way to reach any of the nodes in the next layer, and so on. Yeah? So it starts at the source and then has a front of knowledge that propagates of how much does the cheapest path to any particular node cost. Yeah? So this is Dijkstra's algorithm. and the digression ends here. Good. Now, the obvious question is, okay, so this is an algorithm which works, you know, it's as cheap as an algorithm gets computationally. So again, you know, like with the ILP, we have a hammer, and the question is, can we make our problem look like a nail? And you know, we have already translated our single column problem into you know, something that's linear. I'll give you a final hint before the break. We here had 3 states in my example, classes A, B, C. Here we had 3 nodes in every row, very suggestive. Yeah? So the question is, can we map the problem on top? Can we map this maximum a posteriori problem to a shortest path computation? Okay, and we'll continue with that discussion after the break.